So the time has arrived to begin our study of dynamic programming. So this is a general algorithm design paradigm. As I mentioned at the beginning of the course, it has a number of justly famous applications. However, I'm not going to tell you just yet what it is that makes an algorithm dynamic programming. Rather, our plan is, over the next few videos, to develop from scratch an algorithm for a non-trivial, concrete computational problem. The problem is finding the maximum weight independence set in a path graph. This concrete problem is going to force us to develop a number of new ideas, and once we've finished solving the problem, at that point, we'll zoom out and I'll point out what are the characteristics of our solution which make it a dynamic programming algorithm. Then, armed with both a sort of formula for developing dynamic programming algorithms as well as a concrete instantiation, we'll move on to a number of further and, in general, harder applications of the paradigm. Indeed, even more than usual, the dynamic programming paradigm takes practice to perfect. In my experience, students find it counterintuitive at first, and they often struggle to apply the paradigm to problems that they haven't seen before. But here's the good news. Dynamic programming is relatively formulaic, certainly more so than our recent study of greedy algorithms, and it's something you can get the hang of. So with sufficient practice, and that's exactly what I'll be giving you over the next couple of weeks, you should find yourself with a powerful and quite widely applicable new tool in your programmer toolbox. So let me introduce you to the concrete problem we're going to study over the next few videos. It's a graph problem, but a very simple graph problem. In fact, we're going to restrict our attention merely to path graphs. That's graphs that consist solely of a path on some number n of vertices. The only other part of the input is a single non-negative number per vertex. We're going to call these weights. For example, here's a path graph on 4 vertices, and let's give the vertices the weights 1, 4, 5, and 4. The responsibility of the algorithm is going to be to output an independent set. What that means is a subset of the graph's vertices so that no 2 vertices are adjacent. So in the context of a simple path graph, it just means you got to return some of the vertices and always avoiding consecutive pairs of vertices. So when you have a path of 4 vertices, examples of independent sets include the empty set, any single vertex, vertices 1 and 3, vertices 2 and 4, and vertices 1 and 4. You could not, for example, return vertices 2 and 3 because those are adjacent. That is forbidden. Now, to make this interesting, we're going to want just not any old independent set, but the one whose sum of vertex weights is as large as possible. That's the max weight independent set problem. So what I'm going to do next is use this concrete problem as an opportunity to review the various algorithm design paradigms that we've seen so far. Along the way, we'll see that none of them actually work very well for this problem, and that's going to motivate us to devise a new approach, and that approach is going to turn out to be dynamic programming. So there's always our standard punching bag, brute force search. This would entail iterating through all of the independent sets and remembering the one with maximum total weight. Of course, it's correct, no question about that, but as usual, this would require exponential time. Even in just a path graph, the number of independent sets is exponential in the number of vertices n. So what other algorithm design paradigms do we know? Well, we just finished a big segment on greedy algorithms. We could certainly think about that. You know, pretty much most problems, it's easy to propose greedy algorithms, and this one's no exception. I think the most natural greedy algorithm you might try to use to compute a maximum weight independent set would be, well, what's the myopic decision? Well, you want to get as much weight overall, so at each step, you want to just pick the vertex with the highest weight that you haven't already chosen. Now, of course, you have to worry about feasibility. Remember, we're not allowed to output adjacent or consecutive vertices, so if any vertex is ruled out by adjacency, we ignore it. And amongst those that preserve feasibility, we include the highest weight one in our set so far. Well, let me redraw the 4-node path graph we had on the last slide, and let me ask you, what would this greedy algorithm compute on this 4-node path, and how does that compare to the optimal solution, the independent set with the maximum total weight? So the correct answer is the second one. Let's see why. So let's start with the optimal solution, the max weight independent set. Remember, independent sets are forbidden from choosing adjacent or consecutive vertices. So in this case, the only sensible solutions to consider are the first and third vertex, the second and fourth, or the first and fourth. Of these, the best is the second and fourth for a total of 8. So what about the greedy algorithm? Well, we just had this period of time where we got really spoiled with the success of greedy algorithms, especially in the minimum spanning tree problem. But let me remind you, greedy algorithms, they're often good heuristics. They're often not guaranteed to be correct. And so I'm happy to have this opportunity to quickly remind you again of that drawback of greedy algorithms. They're quite frequently not correct. So this is another such case. So what would the greedy algorithm do? Well, it begins by picking the max weight vertex overall. So that would be this vertex with weight 5. That, unfortunately, blocks the algorithm from picking either of the two vertices that has weight 4. The only remaining option that preserves feasibility is to pick the vertex of weight 1. So that gives us an independent set of weight 6. So this greedy algorithm is not correct. You could, of course, try to devise other types of greedy algorithms, but I don't know of any greedy approach that will actually solve this problem optimally. So that's a bummer, but we still haven't exhausted our algorithm design paradigms. Remember, we learned this quite powerful divide and conquer approach early on in part 1 of this class. And, it seems like it could work here. We had all these successful applications where the input was an array. We broke it into 2 halves. We recursed on both sides and combined the results. And here, path graphs don't look so different than an array of numbers. So the obvious approach for divide and conquer is to break the path into 2 paths, each of half the length of the original, recursively compute a maximum weight independent set in each, and then somehow combine the results. But the issues with the divide and conquer approach are already apparent just in our simple 4-vertex example. So if we recurse on the left half, that is the first 2 vertices, and we compute a max weight independent set, that's just going to be the second vertex by itself. And if we independently recurse on the right-hand side, on the vertices 3 and 4, the maximum weight independent set on the right half is going to be the vertex of weight 5. And now when the recursion's complete and we get our subsolutions back, we have the second vertex and we have the third vertex, but the problem is the union of those 2 solutions conflicts, right? We cannot simultaneously output the second and third vertices. Those are consecutive. Those are adjacent, and that's not allowed. Moreover, in a 4-node graph, it's sort of easy to see how to repair this conflict. But in a big graph with, say, thousands of nodes, if you have a conflict right where the 2 subproblems meet, it is not at all obvious how you would quickly fix that and get a feasible and optimal solution to the original problem. Now, in some sense, the divide and conquer paradigm is more powerful or better suited for this problem than the greedy approach, in that I do know of divide and conquer algorithms that could solve this problem optimally, that run in quadratic time. But doing better than that in a divide and conquer matter seems quite challenging. And in the dynamic programming-based algorithm we'll develop, we'll solve the problem in linear time. That's coming up next.